Okay. Okay, so today starts our third module, and it's basically going to be looking at cost-benefit analysis of behavior. So, I mean, I've sort of titled it here the Behavioral Ecology Toolbox, but there's a series of different approaches used to examine animal behavior that will allow us to assess the sort of adaptive significance of that behavior. So remember, when we think a little bit about those sort of four levels of questions, and we're examining, this course is focusing mostly on questions related to the fitness consequences of behavior. That is how behavior is adaptive and how it relates to individual fitness, that is lifetime reproductive success. And so in order to sort of assess behavior in that context, we need to use a couple of different approaches. I can call them tools, I suppose, that would allow us to assess the adaptive nature of behavior. And we can make predictions about what we expect behavior to be based on some of these approaches. So these are the four aspects that we're going to be looking at. We'll start today by looking at cost-benefit analyses, and then we'll talk about trade-offs, optimality, constraints. Those are all four terms that you should become familiar with as we go through the course. The idea of a cost-benefit analysis is actually a very, very important one, not just in sort of behavioral ecology or in animal behavior, but also in terms of evolution at large. But we'll focus, of course, on behavior. So you'll recall this figure. I showed it to you, I think, probably near the beginning of the course. This is a graph that shows the sort of distribution of males and the amount of time they spend calling. And you remember that with crickets, these crickets, the males will call in order to attract females. And females, the longer a male calls, the more attractive they are, the more females they will attract for mating. And yet, you see here, we have a whole bunch of males that are calling for a relatively shorter period of time. And you can ask yourself, are these males therefore behaving maladaptively? If females prefer males that have that call for longer periods of time, why do some males only call for a shorter period of time? And that is, we're going to ask questions about cost-benefit analysis and so on that will help us understand why that happens. Okay, so, and this is the thing. So every trait, and of course, in this case, we're interested mostly in sort of complicated behaviors like behavior, but there is a fitness benefit and a fitness cost to the individual that's performing the behavior. So that is that, of course, when a cricket calls, it is attracting a female to mate. The longer the male calls, the more females it might attract, or the more attractive it makes itself for females. And so that is the benefit. But there is also a cost associated with that call, right? Like calling has a cost that's associated with the energetic output. So how much energy it costs to make the call for that long period of time. And in addition, the call can be costly in terms of attracting unwanted attention. So not just the females, that is that the males can make these calls and of course is going to attract females, but it might also attract predators, right? So, these are the costs associated with with this behavior. So you have to think about these kinds of traits, behavioral traits in particular, in that context, that they are obviously, behaviors are evolve in order to enhance reproductive success and survival. But that doesn't mean that, every individual is going to perform maximally because of these costs. And again, the costs include the energetic costs, in this case, for calling for a long period of time, and the costs associated with, attracting predators, for example. So there's risk associated with it. Okay, so here you go. I've just sort of, articulated what's been written here. So again, the benefits: higher probability of attracting a mate, higher probability of mating. The costs: increased energy use, likelihood of attracting predators. And one thing that I didn't mention is that a cost is also, if you're spending more time calling, it means that there's less time available for foraging, right, or feeding. And so, this is a cost, but also you can think about this in terms of a trade-off. And we can talk about trade-offs a little later, but it's also a trade-off. I mean, if there's a finite amount of time, and that means that there's only a limited amount of time, right? 24 hours in a day. And you are spending, let's see, how long are these guys calling? You're spending 10 and a half, 9.5 hours calling for a female, looking for a mate. Then that means that's 9.5 hours that you are not feeding, right? So there's a trade-off there in terms of time. We can call it a cost here, but it's just that there's less time available for foraging as well. So there's a lot of risks associated with many behaviors, and nothing more so than mating behaviors. And I'm going to show you some videos here just quickly that will sort of reflect that. The first is I'm going to show you this sort of flamboyant courtship behavior that exists in what are called birds of paradise. We're going to see here. Okay. And so these are birds that, they live in East Asia, in these, fairly, dense rainforest type scenarios. And these species have evolved incredibly elaborate mating systems. And I just want you to think about the costs and the benefits associated with this. Okay, and then we'll just quickly, I'll review it after, and we can think a little bit. But just imagine that, just watch this, and then you can think about what I'm talking about. All right, can you guys? I'm assuming you guys can see this. If you can, someone just let me know that you see it.
We can see it. You're good.
Yeah, we're good. Okay, good. Sorry, I just want to be sure before I hit play here.
The character of the forest changes as you descend, becoming ever darker and damper,
So
favoring different kinds of animals and plants.
You're hearing David Attenborough, of course. I put a link to the video and so on in the D2L as well.
But even here, there is extraordinary variety. In the great island of New Guinea, there are 42 different species of birds of paradise, each more bizarre than the last. This forest is so rich that nourishing food can be gathered very quickly. That leaves the male six-plumed bird of paradise with time to concentrate on other matters, like tidying up his display area. Everything must be spick and span. All is ready. Very impressive, but no one is watching. The superb bird of paradise calls to attract the female. and he has more luck. But what does he have to do to really impress her? She retires to consider her verdict. It's hard not to feel deflated when even your best isn't good enough.
Okay, just a couple of things to point out from there. The first is that Attenborough mentioned that there's lots of food on these islands, so that implies that energy is not as limiting, right? So that allows for the for these birds to have enough energy to grow these elaborate feathers and so on. So just to you saw images and pictures there of many different types of birds of paradise. Most of them were males. It's the males that seem to develop these extravagant secondary sexual traits, which are these feathers and colors and so on. Those are not energetically neutral. What I mean by that is that simply that it costs a lot of energy for those males to grow those feathers, to grow, to engage in those behaviors. And that is possible, at least in part, because it seems that there's lots for them to eat on those islands. So first of all, of course, clearly there's a benefit. The benefit would be to attract females to mate, and that's the point of those behaviors. That the costs are that it's energetically expensive. Again, it sounds like there's enough energy there, food to fuel that behavior. But the other aspect is that it is, many of the colors certainly, and many of the behaviors, and the one we saw there is one aspect, but there are all kinds of other species that have even more elaborate behaviors in terms of, courtship. And it could attract predators. And so, you might make a prediction, and I don't know what the answer to this is, but my prediction is that, active predators must be relatively rare on those islands, because those birds seem to be emancipated from the costs associated with predation, because they're able to evolve these remarkably elaborate behaviors that under normal circumstances would attract potential predators. And I'm going to give you another example here of that. So one other aspect of mating sort of behavior and so on is male-male competition. And so we'll talk about sexual selection and all of that stuff related to behavior later on in the course. But you also have, it's a cost associated with that kind of male-male, behavior, that male-male competition, that it leads to, it also has costs. So this is not, great video. This is actually a video from Africa. So actually what you should do is you should go on YouTube, and there's a lot of videos of people who have gone on safari, and there's plenty of pretty spectacular videos of wildlife. And this one is pretty interesting. So these are, I think, probably Thompson's gazelles, and you can see them fighting. Now, as I said, the quality of the video is not great. And again, I'm assuming you can watch this, but I want you to see, you can see the two males here are sort of sparring, and then you're going to see a dot in the background, okay? And then you're going to listen to these, I think they're German tourists that are going to be describing what's happening.
They can see already.
They're in the fight.
But you can see that the males are not paying attention. They're only fighting each other because they want to mate. And then here we go.
They don't get it.
Just wait, just wait.
Just wait.
Just wait, just wait, just wait, just wait. Ah, it's
Oh my
over.
god.
It's over.
I suppose I shouldn't laugh.
It's over. It's over. It's over. It's over.
But this is an example of a cost, right? So the cost of that behavior, that male, competing, fighting, there's a cost associated with that because it makes them vulnerable to predators. There's also other costs, associated with this kind of behavior. And I'm just going to show you another a video here. So I'm going to show you two. These are bisons that are fighting. So, I mean, another cost associated with this kind of, competitive behavior is the risk of injury, right? And so I'm going to show you two short videos about this.
Takes a heavy toll on the big bulls. So arriving now could give this young contender an edge. But there's life in the old bull yet. To head, the challenger more than holds his own. He makes a small mistake. Shunted aside, his challenge is brutally ended. The young bull gambled everything and has paid a heavy price.
So again, this is just showing you, obviously there are benefits, and this is so the bison is a species where the male has a harem of females, and that male then mates with those females, and so there's a benefit to fighting off rival males. And the rival males, like the young male there's a benefit to fighting, because if he can defeat the male that sort of controls the harem, then he would get to mate. And so there are, reproductive benefits. But just to show here that there are also costs that need to be that are associated with this. So the costs are the energy required to, defend and or be the aggressor in here. And also there's a very real risk of injury. And I've got one last one here to show you that will exemplify this. These are alpacas that I'm going to show you. And these are, basically they are, hyper aggressive llamas in South America. And so they don't have the same kind of weaponry that the bisons have. That is, the big heavy heads and the horns. But as you'll see, they also are able to inflict pretty nasty damage on each other. And again, this species also has a similar system. That is that the males have a harem, a bunch of females that the males kind of defend from other rival males. And the idea is that they're able to mate with those females that they're defending, but there are always, rival males trying to take over and to mate with those females. And so these, the sort of the guarding males are the ones that they have to work very hard to keep that from happening. So we'll just let you watch this here.
One bachelor makes his move. The female spits her disapproval. leaps into action. Using razor-sharp teeth, he aims for his challenger's testicles, an emasculating bite. Necks are protected by specially thickened skin. These fights have no rules. The battles are exhausting. The challenger is driven off. His masculinity intact, the male enjoys the rewards whilst he can.
I hate the very dramatic wording of much of these videos. But anyway, you get the point here that these are behaviors, these aggressive behaviors, for example, in this case, are, obviously there are benefits because the males are trying to, they're trying to breed. Obviously, from a reproductive perspective, those are, or from a fitness or Darwinian perspective, that's an advantage. That's a benefit, but it is also incredibly costly to perform, to do that, right? To protect those, protect, I say, but I mean, to sort of protect their ability to mate from other rival males. And so, yeah, so that becomes, I just want, the point here is just to give you a sense of the costs and benefits of various behaviors. Okay. Okay, so I've given you, right. Okay, so sorry, I'm just working my way through this slide deck. Right. The costs, these costs that I've already alluded to this are the result, at least in part, because of the fact that energy and time are finite. That is that there is not an infinite amount of time. There is not an infinite amount of energy. And so, in terms of, animals, often they have to make what are called trade-offs. They have to, I'll say decide in quotes, because this is done in an evolutionary perspective, but they have to decide on what behaviors to spend their time on. So as it says here, resources spent on one behavior necessarily means fewer resources available for other behaviors or tasks. So again, so thinking about those crickets that are calling, as I mentioned before, like the longer they're calling, that means that there's less time for feeding. The same thing with, these males that are fighting off rivals. The more time they spend doing that, the less time there is for them to be feeding, right? So they're expending energy fighting off and chasing off rival males, but, the cost of that is that they are spending less time feeding. And so therefore there's this whole, this is a trade-off that's that between those tasks, right? In a sense, those behaviors, it's either foraging or fighting off these rival males. So yeah, so here's a couple of examples. I've already sort of alluded to some of them, but energy spent attracting mates means there's less energy available for foraging, less energy to use for somatic repair and maintenance. So if you're spending a lot of energy, for example, chasing rival males, that might mean that there's less energy for, wounds, for wound healing, for, just basic body maintenance to maintain, body fat and things of that nature. It just means that there's less energy available for that kind of maintenance. And, even if we think about parental care behavior, If you're spending time carrying for young, that means that there's less time available for foraging, less time to defend any particular territory, and less time available to find other mates. So we'll talk a bit more about this when we talk about the evolution of mating systems. But what's interesting is to think about, from the male perspective, like, they can invest in raising offspring, and if they're doing that, then that means that they're not out mating and perhaps procreating or reproducing with other females. And so there's a cost benefit there, right? So, depending on the species, if the female can raise the offspring without the assistance of the male, then, these kinds of trade-offs are made in the direction of, abandoning the female and ultimately mating with other females. And this is sort of exemplary of sort of polygynous mating systems and so on. And we'll talk a bit more about that, but just to give you a sense of the kinds of trade-offs that might occur. So this is a cost curve. So we're going to look at some of these graphs. It's going to be important to sort of understand them. So the first here is this. This is the cost curve of, in this case, the amount of time spent singing. So this is again referring to those crickets. And so you have, along the x-axis here, you have 0 to 10, let's say, hours. And then you have a fitness value in terms of cost. So that could be an energetic cost. And so, this cost curve is often exponential. It increases continuously from, in this case, from 0 to 10. So the longer the time spent singing, the more costly it is. This is a benefit, this is the benefit curve. And what is the typical pattern for benefit curves? So this is the fitness value of the benefit along the y-axis. The benefit often, and on the x-axis again is the time spent singing. But usually with benefits, you can accrue them up to a point where they reach an asymptote due to what's called diminishing returns. And what that means is that the more you invest in this case, time spent singing, the benefit of investing more starts to decline, right? So the relative increase in the benefit compared to how much time spent singing becomes minimal. So in this case, for example, the more you sing, of course, that means the more likely you're more likely to mate. But if you sing, say, 5 hours versus 6 hours, the increase in the benefit is not as great than if you were to sing, if you're increasing the amount of time you're singing between 1 and 2 hours. And so you end up with, again, this is called diminishing returns. So that means that you're investing time in singing for longer periods of time, but the benefit that's coming back to you is somewhat reduced compared to if you were singing for just, say, an hour less, for example. And that's the result of this asymptotic curve, right? So the curve is reaching an asymptote. So there's some kind of ceiling on the benefit that you can accrue. Okay, so when we think about cost-benefit analysis, what this means is that we need to look at which point in this case, at which point in this, if we're again considering these crickets and the time spent singing, what is the optimal amount of time spent singing? What is the time spent singing in which there is the maximum difference between the cost and the benefit? So imagine, here we've got the cost curve that's increasing continuously over time. So in terms of time spent singing, and then we have the benefit curve. And as I mentioned, it has a period here of diminishing returns after a certain point. Now, S, just to go back here, S is just a reference to the amount of time spent singing. It's kind of, whatever value you are interested in. But this S star here refers to the optimal, in this case, the optimal trait value. So in this case, this is time spent singing. It's a behavior. So the optimal time spent singing is at this point here, because this is where there is a maximum difference between the cost curve and the benefit curve. Okay, so this is where you have maximized the fitness of this behavior. All right, so I mean, if you know calculus, this will be, you know, you could use calculus actually to calculate these things, but all to say that this fitness sort of this point here, S star, is the optimal time spent singing that maximizes the benefit minus the cost. Okay, so it just maximizes that difference in the fitness value of the cost and benefit. So for any trait level S, you should be able to have a net, you'd be able to calculate a net fitness payoff, and that is simply the benefit minus the cost. So if you were to say, for example, look at S, you know, let's say the time spent singing that's a bit like longer than this optimal period, a cricket could certainly spend its time singing longer than what is predicted to be optimal, but it would not accrue the same you know, net benefit than if it were to call for a shorter period of time, because the costs are increasing and the benefit does not increase at the same rate. In fact, the benefit is starting to, you know, you have those diminishing returns. Okay, so that's why, you know, this is sort of what we might call the, you know, we call the optimal trait value. In this case, the time spent, that's a behavior, time spent singing. Okay, so the optimal trait value, this S star, for a given individual in a given context is the one that maximizes the net fitness payoff derived from the behavior. So the net fitness is, you know, the benefit minus the cost at any given sort of position along this x-axis. And so when you're able to maximize that difference between cost and benefit so that you have maximum benefit, then we can consider that the optimal trait value. Whoops. All right. So this is an important concept to think about and to understand. The idea that the optimal trait value occurs when you have the maximum net benefit, right? The maximum net fitness payoff. And that net fitness payoff is the benefit minus the cost. Okay, any questions about that? It's a fairly important concept to have and to make sure you understand. All right. Optimality theory assumes that what we're seeing reflects this sort of maximized fitness benefit. Sorry, yeah, this sort of it assumes that that in a population of animals that are, you know, engaging in whatever behavior, that those behaviors are have become adapted, and therefore that means that the behaviors that are being performed are maximizing that net fitness benefit, right? And this is because evolutionary theory predicts that traits seen in populations at equilibrium will be those that maximize lifetime reproductive success. All right, so we make this underlying assumption that animals behave optimally. Now, that's not always the case, and I'll explain some examples of why that might not be the case, but we assume that populations are at evolutionary, what we call an evolutionary equilibrium, and that individuals in that population are maximizing their net fitness when they behave. So this approach, you know, obviously applies to sort of what we call fixed traits. So these are things like body size and so on, but it also applies to the kinds of traits that we're interested in, behavioral traits. And the thing is that when we make these predictions about equilibrium, and we make predictions about, hang on, I just earlier we talked a little bit about context. Hang on a second. well, I can't find it. But what's important to note is that when we talk about behavior and we talk about optimality theory, that we're dealing with behavioral traits that, and the context that an individual finds itself in can change rapidly. And so that means that, behavioral traits and what is optimal can change much more, is much more likely to change than any other trait like, body size and things of that nature. So this is, we'll talk a little bit about decision rules later on, but this is the thing, is that the context in which an animal finds itself is changing relatively rapidly. And so you end up with changing optimal values for behavioral traits. So what is optimal can change from like one day to the next, depending on, the relative amount of food that's available in the environment. It might change depending on whether there's lots of food or not a lot of food, right? So those, the amount of energy that's available in the environment for a given individual animal may result in changes in behavior. And so these are not static, I guess so what is optimal is not static and can change, as I said, depending on the context. So here we go. So optimality theory, there's, well, if you're like my brother and took economics, you can talk about this too. In economics, they talk about optimality theory too. So much of what I'm talking about here is also relevant to behavioral economics. So if you've ever taken a course in that, you'll note that much of the language that is used in behavioral economics is actually very similar to what we've just been describing. That is talking about trade-offs, talking about optimality, and so on. In this case, there are 4 parts to this perspective of optimality theory. The first is that you have to identify a behavior of interest and the range of possible strategies. So we can call these decisions. Now, that doesn't mean that animals are necessarily making conscious decisions, but nonetheless, from an evolutionary perspective, these are decisions that are made by animals. Very importantly, you need to come up with a common currency for costs and benefits. So if we're going back to, let's say like this particular graph, and we have, some here on this fitness value, sort of this behavior here, this is time spent singing, and we're talking here about the fitness value in terms of costs and benefits. What's really important is that the currency or the units in terms of costs and benefits are the same. Otherwise, you can't compare them. So this is important, that we are able to assess a common currency for costs and benefits. So often the costs and benefits are reflected in terms of reproductive success, how many offspring are produced perhaps, or in terms of energy, right? How much energy is acquired and how much energy it costs to perform a behavior and so on. So this is important though, that this common currency, which specific fitness component is affected by the behavior. And answering this question helps us determine what is the common currency for costs and benefits. We have to consider intrinsic and extrinsic constraints on performance. So intrinsic means things like how much energy the animal is carrying and is available for it to perform any particular behavior. Extrinsic constraints include things like the presence of predators, the presence of competitors. So those are other constraints on performance. So intrinsic and extrinsic. And then you have to test the optimization model predictions. And so we'll go through what that means in a minute. Now, here are the underlying assumptions. And I've sort of alluded to these already. But the first assumption is that all possible solution strategies, all possible strategies are available to the animal of interest. So what that means is that we assume that if there was a trait, a behavioral trait that was, that would maximize fitness, that over, the evolutionary time of a given organism, that there was genetic variation in the organism that would have allowed for, that optimal behavior to evolve. Okay, so this sort of optimal solution for a particular behavioral problem is possible. And so we assume that there's genetic variation over the course of the organism's evolutionary history that would allow for all of these possible solutions to occur. That is, that there aren't any constraints on the evolution of these optimal solutions, if you will. The other assumption is that the population is at an evolutionary equilibrium. And what that means is that the optimal solution has been reached. That is, that the existing population of animals that you're looking at are adapted for the environment that they're in, and therefore that means that the way they're behaving is already optimal. Now, there are reasons for these assumptions to be violated, right? So, for example, if you have a species, an animal that is an invasive species and it has invaded a habitat or a landscape that is novel to it, then that population is not at an evolutionary equilibrium, and so you might not expect that the behaviors of those animals would be necessarily optimal. So there are, situations where this evolutionary equilibrium is not reached. And so we have to be cognizant of that. Okay. I'm going to just talk a little bit about one set of behaviors, and we'll just finish off with this. It's going to be a few slides. So these are birds, clearly. Many birds, when they're feeding or foraging, they will forage on food items that are hard, physically hard. And so, they have to crack them open somehow. And, birds lack hands, they lack opposable thumbs, and they're not able to normally crush, these kind of hard food items themselves. And so they have to employ what's called prey dropping behavior. That is, that they fly up into the sky and they drop whatever it is that they're trying to break, and they'll drop it and then fly down and try, if it's not cracked, or they'll do it again until it opens. And so here's some examples. Many of these are from what are called corvid birds. These are ravens and crows and their relatives, and they are very, very smart. And they, you'll see, I'll show you an example in a minute. They're able to do this kind of behavior. So here's a series, like American crow, nuts, mollusks. So like shelled invertebrates. You see lots of examples here. Turtles. So cracking open a turtle shell by dropping it. Herring gulls will do it to invertebrates again, and even, I guess, fish, although I don't know how that would happen with fish. But finally, eggs. So here's a great black-backed gull can do that with eggs. All right, so I'm going to show you a video here. Hang on a second. So this is a short video. Again, it's not it's not terribly good. The pixelation's a bit high, but anyway, it's again David Attenborough. So just watch it. It's a couple minutes.
Crows have become highly skilled at making a living in these new urban environments. In this Japanese city, they have devised a way of eating a food that normally they can't manage. Dropping a nut from a great height onto a hard road does sometimes crack it, but some nuts are particularly tough. So the crows have devised a better way. Drop it among the traffic. Problem now is collecting the bits without getting run over. So some birds have refined their technique. They station themselves beside pedestrian crossings. Wait for the lights to stop the traffic. Then collect your cracked nut in safety.
Okay, so I mean, I show you that video because it just gives you a sense of how this kind of this kind of behavior can ultimately evolve. But it essentially what I'm trying to show you here is that there is that these birds are they evolve behaviors to allow them to crack open these hard food items. And so here is an example. So we're going to try and apply this sort of cost benefit analysis to in this case for these crows, and they feed on what are called whelks. So whelks are a mollusk. It's a shelled invertebrate, and so they feed on, so the whelks, of course, are on the shoreline in sort of marine shorelines, and these crows are feeding on them. And so what they've observed is that they pick relatively large whelks, and they will fly up to 5 meters up and then drop them. And they'll drop them on rock with the idea that the rock, that will lead to them cracking open, and then the crows can feed on the inside, right, where it's all nice and soft. So the question is, why they're flying about 5 meters up each trip. They often make multiple trips, so we can try and apply our cost benefit approach to this whole foraging strategy. So there are decisions that these birds need to make. They have to choose the whelk based on its size. They have to just, repeated attempts at opening a given whelk. They have to fly up into, they have to fly multiple times and drop the whelk until it's cracked. They have to make a decision as to how high to fly, and therefore, there's energy, of course, associated with I should say that there's a benefit in terms of obviously what they're feeding on the whelk. So there's food, but there are costs, that is including how many times they fly and drop the whelk and how high they fly up. So both of those take energy. And so we can think about this, about the trade-offs in terms of this behavior, in terms of calories, for example, how much energy is being used to crack open the whelk, and how much energy is gained by feeding on the whelk. So here is some curves. So this is the number of times that a whelk has to be dropped. This is the height of the drop, and we have both small, medium, and large whelks. We know that, so crows tend to pick the large whelks. So that is the open circle, this black line. Sorry, it's a bit pixelated. So that black line, so this reflects the number of times that the whelk has to be picked up. It takes more, I guess, energy in some ways. I'll get to that a bit more in a second, but you can see that they have to fly at a higher height to drop the larger, I'm sorry, large is in red. My mistake, sorry. Large is in red here. So the red, what this means is that they don't have to fly, it doesn't require quite as many drops. And in particular, it doesn't require quite as many, the height is not quite as high. in order to crack open these larger whelks. The larger whelks are easier to break. So they make multiple trips. They can make multiple trips to break open the whelks. And we need to figure out what is the optimal drop height, let's say. And that's what we're going to try and assess here. So right now we know the observation is they fly about 5 meters up at each trip. We need to decide what is, if we're going to do this cost benefit analysis, what is the appropriate currency in order to assess the costs and benefits. And so this is where I already alluded to the fact that we can look at it in terms of energy or calories. So we can look at the energy gained from a large whelk, which is about 2 kilocalories. And then we can look at the cost of breaking a large whelk. And so this is a function of the number of trips that a bird has to make, number of times it has to fly up and drop the whelk, and also the height of the trip, right? So how high it has to fly. So that the cost is associated with these two. It's a function of these two variables. And this is, I'm not going to go through the math, but this is basically what it looks like. Okay, so this is the benefit. Remember, the benefit is it's static, right? It's the amount of energy that's in a single whelk. And the cost, this is the cost curve here. And you can see along the y-axis is energy in kilocalories. And that's why the benefit is a straight line, because a whelk is, the amount of energy in the whelk doesn't change. And along the y-axis, the x-axis is the height of the drop. Okay, now, this D is around 5.6. What does this mean, D star? The D star is the optimal height, okay, that it's being dropped at. And I have to say I moved it over a little bit. So this dashed line should actually be right here underneath the arrow. But again, so imagine that the reason that this curve looks this way is in part because it takes a lot of energy for the bird to jump up into the air. And then, it flies, and then it takes up more energy. So at some point, when it reaches around 5 meters, it actually, the amount of energy required to be held aloft is a minimum value. And then that value increases as the bird has to fly higher. So at this point, the maximum difference between the cost and the benefit here reflects the optimal height at which the whelk should be dropped, right? Because it means that the relative cost is minimized in relation to the benefit here. So this is the point at which the benefit and the cost are maximally different from each other. And therefore that means that this is the point at which these crows are getting the maximum caloric intake, the net caloric intake from breaking this and eating this whelk. All right, so this explains why these crows tend to fly up to about 5 meters in order to drop the whelk that they have selected. So there are, so I think we'll stop there, but just to make a point that the costs and benefits may vary due to aspects of the abiotic environment. So, imagine like wind speed, right? If it's a windy day, that will increase the costs of flying. And therefore, that means that this cost curve could change, which means the optimal height at which to drop the whelk could be different because of the presence of the wind, let's say. Social environment. Imagine if there were other crows trying to steal the whelk that had been dropped. So that also may alter this cost curve, which also therefore may alter the optimal height, right? Individual genetic qualities. So whether, perhaps some of these crows have, let's say, shorter wings, and therefore the energetics of flight are slightly different. And that may also change this cost curve, and therefore again change that optimal height. So different crows may have different optimal heights depending on the energetics of flight associated with their physiology or individual morphology. Individual condition, right? So some, again, this speaks just simply to the fact that some individual crows in this case may be heavier than others because they're already carrying a lot of extra fat, for example. And again, those kinds of things may alter that cost curve. And so all to say that there are a series of different factors that can lead to variation in this cost curve, and therefore can lead to changes in what is optimal. And so what is optimal, importantly, what is optimal for one individual may not be optimal for another. And what might be optimal in one environment might not be optimal in another, depending on the cost curve and what it looks like, depending on the kinds of things that I've described already. Okay, we'll stop there and we'll talk a little bit, we'll talk about the crickets, and there's a whole bunch of, I'll talk a little bit more about the effects of competitors trying to steal food in this context. And there's a few other examples we'll go through that will try to explain the cost-benefit analysis. One thing to point out is that the prey dropping behavior, I've got a few examples. So in this case, there's a paper on D2L for you to look at. This is actually the model, and I don't expect you to read it completely and to understand it, but it just gives you a sense of the model associated with the birds dropping food items. And then there's another sort of empirical test that looks at American crows dropping walnuts and the drop height, and also looks at kleptoparasitism, which is when other crows are trying to steal the nuts. And so anyway, it's worth taking a look at those. We'll talk about these a bit more in detail next time. Okay. If you have any questions, let me know. I'll stay online, and otherwise, we'll see you next time.
Thank you.
Thank you.
Thank you, sir.